Good morning to all. So today we will be going to discuss about gear trains. So already you might have studied the concept of gear, classification of gear, etc. So now let's see what a gear train is. So the objective of this session is first to understand the concept of gear train, then the major classification of gear train, what is their necessary equations, their applications, etc. So what do you mean by a gear train? So gear train can consist of two or more gears meshed with each other in a particular way in order to transmit power from one shaft to other. So mostly the gear train will have more than two gears, for example 3 gear, 4 gear, or as the number of gears increases, this will become more and more a gear train. And the nature of train used depends upon the relative position of axis of the shaft and velocity ratio required. And the gears in that gear train may be spur gear, helical gear, or bevel gear. So we can use any of these gears according to our need for the members of this gear train. And another important parameter in gear train is speed ratio. So what do you mean by speed ratio in gear train? So gear train, there will be a large number of gears. So we have to define the speed ratio of a gear train. So it is defined as the ratio of speed of the first driver gear. So we have to take the speed of the first driver gear because there will be a large number of driver gears in that gear train, and similarly a large number of driven gears will be there. So the gear which rotates by itself is known as a driver gear, and the gear which is rotated by some other gear is known as a driven gear. So in this gear train, the speed ratio is the speed of first driver gear divided by the speed of last driven gear. And the reverse of this is known as the train value of the gear train. So train value of the gear train is just the reverse, that is speed of the last driven gear to speed of the first driver gear. Now how will you classify the gear train? Depending upon the arrangement of gears, we can classify into 4 categories. That is, first one is simple gear train, then compound gear train, reverted gear train, and finally epicyclic gear train. So these are the 4 classifications of a gear train. So we will see one by one. So let's first check the simple gear train, what it looks like. Yes, this is a figure of simple gear train. This is a simple gear train consisting of 2 gears. This is a simple gear train consisting of 3 gears, and this is another simple gear train consists of 4 gears. So you can see here the front view is drawn like this. This circles represents the pitch circle of gear. So this circle represents that gear, and this is the top view. So in the top view you can see the teeth of these gears and shaft, etc. clearly. So the shaft will be at the center of each this gear, so it is seen like this more clearly in this top view. So you can see here the 3 shafts here, the 4 shafts here. So why this is called a simple gear train? Yes, in a simple gear train only one gear will be on one shaft. So you can see here this shaft consists of only one gear, this shaft consists of only one gear. So all these shafts will have only one gear. So that is the main idea of a simple gear train. There will be only one gear in one shaft. And the intermediate gears, so first, this is the first driver gear, this is the last driven gear. So the gears between them is called as intermediate gears. So you can use here the first figure, there is no intermediate gear, only driver gear and driven gear is there. In the second figure, we have one driver, the intermediate gear. This is the second one is an intermediate gear. And the third figure, we have two intermediate gear. So what is, you have noticed anything about the number of intermediate gears and the direction of rotation? Yes, when the number of intermediate gears are an odd number, the motion of driver gear and driven gear is in the same direction. So you can see here in the second figure, the number of intermediate gear is an odd number, that is 1. So we are using one intermediate gear, which is an odd number. So you can see here the rotation of this driver and driven gear is in clockwise. So they are in same direction. But what about this first one and third one? So here there is no intermediate gear, 0. But here we have two intermediate gear, another even number. So when the number of intermediate gears are even number, you can see here the driver gear and driven gear rotates in the opposite direction. So here you can see this is in clockwise while this is in anti-clockwise. So because of the gears which is meshed directly will be always opposite rotation. So here 1 and 2 are in opposite direction. Similarly here 1 and 2 are opposite, 2 and 3 are opposite. So that means 1 and 3 will be in same direction. Similarly here 1 and 2 rotates in opposite direction, 2 and 3 rotates opposite, 3 and 4 rotates opposite. That means 1 and 4 will be opposite direction. So like that we can predict the direction of motion of a driven gear by counting the number of intermediate gears. So when the number of intermediate gears are odd number, the motion of driver gear and driven gear are in same direction. And when the number of intermediate gears are even number, the motion of driver gear and driven gear are in opposite direction. Now we have to find out the speed ratio of this gear train in simple gear train. So now consider this third figure only. So we are considering this figure B for deriving an equation for speed ratio. So it have only one intermediate gear, 2. So first one is the driver gear, last one is the driven gear. And let N1, N2, N3, etc. are the speed in RPM of these gears correspondingly. And T1, T2, T3 are the number of teeth on driver gear, intermediate gear and driven gear. So we have considered only second figure. Now what happens is, since the driven gear 1 mesh with the intermediate gear 2, their speed ratio can be written. So how their speed ratio can be written? Yes, like this, N1 by N2 is equal to T2 by T1. We already studied this. Two intermeshing gears, the speed ratio is inversely proportional to the number of teeth. So we have studied this in the earlier session. So we can write this for 1 and 2 because 1 and 2 are directly meshed here. Here we can see it is meshed here. So N1 by N2 will be T2 by T1, in inverse of their number of teeth. So that's this be equation 1. Similarly, intermediate gear 2 and 3 mesh together. So in this intersection, we can see 2 and 3 are meshed together. So again the speed ratio of that two gears. So remember we are writing the speed ratio of this individual gear, each of this gear, and we will be combining these for the entire gear train. So first we have write the speed ratio for 1 and 2 which are meshed together. Now we are going to write the speed ratio for 2 and 3 which are meshed together. So that means again N2 by N3 is equal to reverse the T3 by T2. So this is equation 2. Now what we want is the speed, what will be the speed ratio of this gear train, this entire gear train we have already defined. The speed ratio of this gear train will be speed of the first driver gear to speed of the last driven gear. So N1 by N3. So we want N1 by N3. But there is no direct connection between 1 and 3. So we cannot simply write directly like that. But using these two equations, how we can get that? Simply multiply this equation 1 and 2. We can see n1 by n2 into n2 by n3, n2 cancels. Similarly, right side we have t2 by t1 into t3 by t2. So again t2 cancels. So we will be getting like this, n1 by n3 is equal to t3 by t1. So that means the speed ratio in a simple gear train is speed of the driver gear, that is first driver gear, by speed of the last driven gear, which is also equal to number of teeth on the driven gear to number of teeth on the driver gear. So this equation is valid for any number of gears of a simple gear train. So if you have 6 number of gears in a simple gear train, the speed ratio will be n1 by n6, which will be equal to t6 by t1. So like that we can write this speed ratio for any number of, so it holds for any number of intermediate gears. Now what is the importance of this equation? Any conclusion you are getting? Yes, that is the intermediate gear, the size and number of teeth, speed, etc. of intermediate gears are not having any influence in the speed ratio of that gear train. So here you can see this is the speed ratio of this gear train, but there is no n2 in any of this equation, n2 or t2 coming. Both of them get cancelled in this previous equation. So that means there's an important concept. In simple gear train, the speed ratio is independent of the size and number of intermediate gears. So in this simple gear train, these intermediate gears are also known as idle gears. So they are simply idle gears. They does not take parts in this equation. They are not coming. N2 or T2 etc. are not coming. Then why we are using intermediate gears in simple gear train? They are having no effect in speed ratio, but we are using this intermediate gears with the two purpose. So the intermediate gears in a simple gear train used for two purpose. Can you tell what is that? Yes, first one is to obtain the required direction for driven gears. So we can change the direction of driven gear clockwise or anti-clockwise by changing the number of intermediate gears. So already we have studied, if the number is an odd number, this will be the same direction of driver gear. So this will be clockwise. And if you want anti-clockwise, so in this figure, this driven gear is in clockwise. But if you want to change it to anti-clockwise, what we can do? Yes, in this same space, instead of this second intermediate gear, we can use two small intermediate gears. So instead of one intermediate gear here, we can use a small two intermediate gears, so that it will become an even number and it will be rotating in the anti-clockwise opposite to this. So that is the first purpose. Then another one, intermediate gears are used for connecting a large center to center distance. Suppose we have to connect this center to center distance of this first driver and last driven gear is too large. So if we are using without intermediate gear, means we have to use a large gears. So suppose if this gear is not used here, how to connect this first and third shaft? Yes, we have to use more large gears, so like this. So it will be a material cost, other loss etc. will be there. So instead of that, we can use a small intermediate gears. So that is a two purpose of using intermediate gears. First one, to get the desired direction of motion of driven gear, and second one, to connect two shafts of large center to center distance, we can use a number of small intermediate gears, so that we can save the material cost, loss etc. So these are the purpose of this intermediate gears or idle gears in simple gear train. Now what are the applications of simple gear train? They are mainly used in automobile gearbox. Already know automobile gearbox have several gears, first gear, second gear etc. In the lathe machine we are also using this, and heavy duty press machine etc. we are using this simple gear train. Now let's go for the compound gear train. What is the difference? So this is a figure of a compound gear train. So have we identified any difference between this and a simple gear train? Yes, you can see here, in a compound gear train, one shaft may contain more than two gears. So if you take this shaft top view of this gear train and see the figure B, shaft B. So shaft B have two gears, 2 and 3. So shaft B, this figure also you can see shaft B is at the center of this hole. So it have two gears in different locations, that is 2 and 3. Similarly, shaft C has also two gears, this 4 and 5. So you can see here 4 and 5 are in gear C, shaft C. So that means compound gear train is different from simple gear train. How it is different? In compound gear train, there will be more than one gear in a shaft. So in simple gear train we have seen that only one gear comes in one shaft. But in compound gear there will be more than one gear in a shaft. So this is an example of compound gear train. So you have to draw this figure while deriving the speed ratio of this gear train. So what is this figure? This figure, gear 1 is mounted on shaft A. You can see here gear 1 is mounted on shaft A. So here only one gear is there. First gear is on shaft A. First is the driver gear. So this is the first driver gear. Then gear 2 and 3 are mounted on shaft B. So two gears are there on shaft B. Then gear 4 and 5 are mounted on shaft C. So this is shaft C. So we have 4 as well as 5. And finally gear 6 is there on shaft D. So this is the last driven gear. Now what is the motion here? So remember we have some 1 and 2 are directly connected. So 1 and 2 meshed with each other. So you have to refer the top view also, which gears are meshed directly. You may not be easily understand by front view only, because there are a large number of gears and they are on the same shaft. So you have to refer this top view also. So you can see here 1 and 2 are meshed together in this interface. So gear 1 drives gear 2 in the opposite direction. So when the gear 2 rotates, this shaft B will also rotate. So simultaneously the gear 3 is on shaft B, it will also rotate. So you must remember this. The one shaft will have only one speed. So whenever there is more than one gear in one shaft, they will rotate in the same direction with the same speed. So when the 2 rotates, the 3 also rotates in the same direction and same speeds. You can see here 2 and 3 both are in anti-clockwise direction. So as gear 1 drives gear 2 in opposite direction, and gear 2 and 3 will rotate in same direction because they are on a same shaft B. Now what happens? Gear 3 and 4 are connected. You can see here this interface here. 3 and 4 are connected. So 3 rotates the 4 in the opposite direction, again clockwise. So gear 3 drives gear 4 in the opposite direction. Now as the 4 starts rotating, the shaft C also rotates, which is at the center of that gear. And what happens? As the shaft C rotates, the gear 5 will also rotate because 5 is also in that shaft C. So 4 and 5 have is the same direction of rotation and speed. So gear 4 and 5 rotates in the same direction, clockwise. And finally we have 5 and 6 connected or meshed here. So 5 will rotate 6 in the opposite direction. So we must be very careful in this for predicting the direction and how motion is transmitted from 1 to 6. So you have to refer this top view also. And remember, one shaft will rotate only in one speed. So therefore 2 and 3 the speed will be same. Similarly 4 and 5 the speed will be same. Now we have to derive the speed ratio of this gear train. So let's N1, N2, N3 etc. up to N6 are the speed of the respective gears. Similarly T1, T2 etc. T6 are the number of teeth on the respective gears. So we have to consider each intermeshing gears and write the equation similar to what we have done in the simple gear. So let's see. So first meshing is gear 1 and gear 2. So we can write only this equation whenever there is a direct meshing coming. For example, you cannot write this speed ratio between 2 and 4 because 2 and 4 they are not meshed together. But you can write between 1 and 2 because 1 and 2 are meshed together. So since a gear 1 mesh with gear 2, speed ratio is N1 by N2 which is equal to T2 by T1. Similarly, gear 3 and 4 mesh with each other. Here 3 and 4 is meshed with each other. So we can write N3 by N4 is equal to T4 by T3. That is equation 2. What is the remaining gear meshing with each other? Yes, the last one, 5 and 6. So 5 and 6 meshed with each other. So we can write N5 by N6 equal to T6 by T5. So here also we are getting 3 equations. What we want is what is the speed ratio of this entire gear train? Yes, the speed of first driver gear divided by speed of the last driven gear. So we want N1 by N6. So in a similar way we have to multiply these 3 equations, multiply equation 1, 2 and 3. So N1 by N2 into N3 by N4 into N5 by N6 equal to T2 by T1 into T4 by T3 into T6 by T5. This is equation 4. Now we can simplify this. We can use this. Since the second and third shaft gears are of the same shaft, they will already be told that they will be having the same speed and direction of rotation. 2 and 3 will rotate same speed. That means N2 is equal to N3. Since gear 2 and 3 are mounted on a shaft B, N2 equal to N3. Similarly, gear 4 and 5 are mounted on shaft C. So N4 is equal to N5. So both are same. So we can substitute these in this previous equation, equation 4. What happens? N2 equal to N3. So it get cancelled. Similarly, N4 equal to N5. So it is also cancelled in the numerator and denominator. So finally we will have only N1 by N6. So by substituting this we are getting N1 by N6 equal to, but the number of teeth will not cancel because they are not equal at all. So it will be as such. So N1 by N6 equal to T2. In the numerator we have T2 into T4 into T6. In the denominator we have T1 into T3 into T5. So this is the equation of the speed ratio of this compound gear train. Or we can generalize that means the speed ratio of a compound gear train is equal to, that is the speed of first gear to speed of last driven gear N1 by N6 here, which is equal to the product of number of teeth on all the driven gears divided by product of number of teeth on all the driver gears. So without writing this equation we can write the speed ratio. How? So speed ratio N1 by N6 is, first you have to take the product of number of teeth on all the driven gears. So what are the driven gears here in this figure? Driven gears means that rotates not by themselves but rotated by other gears. So they are driven gears are rotated by other gears. So what are they in this figure? Yes, the 2. 2 is rotated by 1. So 2 is a driven gear. Similarly, we have 5, this 4. 4 is rotated by 3. So 4 is another gear. Similarly, 6 is rotated by 5. So that is why T2 into T4 into T6 comes in the numerator divided by product of number of teeth on all the driver gears. So what are the driver gears in this figure? Yes, gear 1 rotates by itself. So it is a driver gear. Similarly, gear 3 is rotated because of the rotation of the shaft B. So when T3 is there. Similarly, 5 also rotate by itself. So that is the product of number of teeth on all the driver gears. So we can write like that. This is an important equation in speed ratio of a compound gear train. So another important thing is, so in compound gear train this intermediate gears have an important effect on the speed ratio. So not like in simple gear train. In simple gear train we can see that these intermediate gears are used only for two purposes. One is for changing the direction or rotation of the driven gear and for connecting large center to center distance. But here you can see here they have an effect on the speed ratio. So in compound gear train the purpose of the intermediate gear is intensified, so that we can see that the speed ratio can be increased or decreased by changing the intermediate gear. So if you want to increase the speed ratio, what you have to do is you can increase the intermediate gears in this numerator or decrease the number of teeth in the intermediate gears in the denominator. So like that we can change the speed ratio without changing the first and last gear. If you change the number of intermediate gears and their teeth, etc., diameter, etc., we can change the effective speed ratio. That is the important conclusion we are getting in compound gear train. Now it's the application also there in lathe, clock, watch, etc. We are using this compound gear train. So that is about compound gear train. So you must be very careful in writing the equation. So you have to first draw this neat figure, then write equations one by one and obtain the speed ratio n1 by n6. Now we move on to the third one, that is reverted gear train. It is a special type of compound gear train. So this is also a compound gear train. What is the difference here? So here you can see two gears are on this second shaft, 2 and 3. And the difference is here the shaft of the first driver gear and the last driven gear are coaxial. They are on the same axis. So that is, it is a special type of compound gear train where the axis of first driver gear and the last driven gear are coaxial. So there you can see here, they are not the same shaft, but this is two shafts. So gear 1 is in one shaft, gear 4 is in another shaft, but they are same axis. They are parallel or the axis is same. And this is a compound gear, 2 and 3 are on the same shaft. So where you have any example for reverted gear train, just think about this. Whether we have identified anything that is so that the driver gear and the last driven gear are on the same axis. As if you look at your watch, clock, etc., the minute hand, hour hand, etc., are having the same axis. So that is an example for reverted gear train. So what will be the equation for this? Gear 1 rotates gear 2 in the opposite direction, and gear 2 and 3 are mounted on the same shaft. So 2 and 3 will rotate in the same direction. Gear 3 and 4, 3 drives the 4 in the opposite direction. You can see here 3 and 4 are connected. So 1 and 2 are connected, 3 and 4 are connected, and 2 and 3 are on the same shaft. So this equation we need not have to derive again because this is also a compound gear train. So the equations will be same. Only thing is the first shaft and last shaft are coaxial. And eventually gear 1 rotates 4 in the same direction. So that is why it is used in watch, clock, etc. So by using this arrangement we are getting 1 and 4 in the same direction. So in watch, clock, etc., the minute hand, hour hand, all the hands will be rotating in same direction, that is clockwise. So like compound gear train also, here directly we can write the speed ratio, that is the product of number of teeth on the driven gears divided by product of number of teeth on the driver gears. So what is that? The speed ratio we can directly n1 by n4, first driver speed divided by last driven gear speed. So what will be the product of number of teeth on driver gears? So 1 driven gears. So in the numerator it will be driven gears. Which are the driven gears here among these 4 gears? Yes, 2 is the driven gear because 2 is rotated by 1. Similarly 4 is another driven gear because 4 is rotated by 3. So T2 into T4 divided by what will be the product of number of teeth on driver gears? Yes, T1 is another one driver gear, rotates by itself, and T3 is another driver gear, rotate by itself. So T1 by T3. The speed ratio is N1 by N4 is equal to T2 into T4 divided by T1 into T3. And another equation also we can write in this reverted gear train. That is, if you take the center to center distance between these gears, they are same. That is, the center distance between gear 1 and 2 as well as gear 3 and 4 are same, because they are only same, distance between them are same. So we can write this one also, d1 plus d2 also equal to d3 by d4. So if you add the diameter of this pitch circle of these gears, that is 1 and 2 and 3 and 4, they are same. d1 plus d2 equal to d3 plus d4. So that means when the diameter is, we can write like this, and if their pitch will be same because they are meshing with each other, 1 and 2 are meshed together, means their pitch must be same. Similarly 3 and 4 mesh, their pitch must be same. So we can write this one also, T1 plus T2 equal to T3 plus T4. That is, if you add the number of teeth of 1 and 2, it will be the same of the number of teeth of 3 and 4 added together. So this is an additional equation you can use in this reverted gear train, T1 plus T2 equal to T3 plus T4. And where it is applied, it's already we have discussed, it mainly applied in clock, then lathe back gears, automotive transmissions, industrial speed reducers, etc. Now we are going to the last gear. This entirely different gear, a epicyclic gear train. So you can see here this entirely different gear. So what do you mean by epicyclic? So it's a Greek word. The word epi means upon and cyclic means around. So that means in epicyclic gear train, the one gear will be moving upon and around another gear. So you can see in this figure, the gear B, not only it will rotate in its position, but it can move around this gear A. So such a gear train is known as epicyclic gear train. So in epicyclic gear train, the arrangement of gears are in such a way that one or more gears can move upon and around another gear. So if it is like that, if any one of the gear can move around another gear, it is known as an epicyclic gear train. And have you noticed any difference between this and what are other three gear trains? Simple gear, if you consider simple gear, compound and reverted, and this gear train, what is the difference here? Can anybody tell that? Yes, here the axis of rotation can change relative to a fixed axis. So that means here this is a two axis, this is one axis, this is another axis. So that we can change. If the gear B can move around gear A, the relative position between this axis will be changing. So that is an important thing in epicyclic gear train. In epicyclic gear train, the axis of shaft in which gears are mounted can move relative to a fixed axis. But in all the other gear train, they are fixed, they cannot be moved. The axis of the gears are fixed. In any point there will be same constant orientation, but here they can move relative to a fixed axis. Now in this figure, what you can see is gear A and arm C have a common axis at O1. So gear A and this arm C. So we have gear A, B and arm C. So gear A and arm C have, here it is having the same axis at O1. And gear B engage with gear A, and they have a common axis at O2 here. Now two types of motion is possible. What is that? If the arm is fixed or static, suppose this arm is fixed, or we are using some nut and bolt or something like that to fix the arm at O1 and O2, then it will be only a simple gear train. That is, the gear A will drive gear B in the opposite direction only, or the gear B can drive gear A. So if the arm is fixed O1 and O2, this will be acting as a simple gear train only. The gear A will rotate only gear B. No other motion is possible. But if the arm is free and the gear A is stable and the arm is free, what will happen? The gear B can move rotate upon and around gear A. So if it is not fixed here at O2, this gear B will be moving upon and around this gear. So that is the important thing of epicyclic gear. So it can move upon and around. Now where this is applied, so the main application is in the differential gear of an automobile. So already we have discussed in the previous class what is a differential gear. Differential gear is used for taking a curvature in a vehicle, four-wheeler, etc. We require the inner gears to be at less speed compared to outer gear. So in that we will be using this epicyclic gear train. Similarly in hoist, pulley blocks, wristwatch, etc. we are using epicyclic gear train. So that is an application of epicyclic gear train. So we are stopping this session. So this mainly asked question in university exam, explain gear train and their classification. So you have to draw a neat figure in all this case, write the equations required, speed ratio, etc. Explain the mechanism and write the application. So thank you.